much, everyone, for joining today. We have Allison Goodwell. She's a visiting associate research scientist at Prairie Research Institute at UIUC in Illinois. And Allison will be talking about information decomposition, causality, and ecohydrological model evaluation. So thank you, Allison, for being here, and the floor is all yours.
All right, great. Thanks, Layla, and have a good time at your conference. All right, so hi, everyone. Today, this is kind of a presentation that I volunteered for 7 or 8 months ago, and then I had to cancel, so then I put myself much farther ahead on the schedule. I think it was like, last February I had to cancel, and I totally switched the paper and switched the topic because about a month ago, I just kind of realized, it was a paper that I'd read a long time ago. But anyway, the main things that I want to talk about today are causal inferences and specifically information decomposition-based approaches to look at that. And I also wanted to tie it into model evaluation and how we might think of models in terms of how they represent causal processes. And so I did the easiest thing there, which is to bring in one of my own papers. And so I'll kind of tie in the topic with ecohydrological modeling. Whoops. All right, there we go. This is just the abstract of the main paper. Basically, it focuses on causality and states that it's kind of at the heart of scientific inquiry, and it's the basis for how we seek to understand how physical systems are working. However, it's really hard to do, particularly based on observational data, because we have a lot of different types of systems. We have linear or nonlinear systems, we have stochastic or deterministic, we have feedbacks and self-causation, we have external factors, colliders, confounding variables. There's a lot of different types of interactions that could be occurring, and different methods have challenges kind of disentangling those different types of interactions. So this paper particularly proposes a method that they call SURD, and SURD stands for Synergistic Unique Redundant Decomposition of Causality. So that might be familiar to quite a few of you here, or at least the general ideas of synergy, uniqueness, and redundancy, but they kind of build on the existing framework for that decomposition and compare their causal inference method with some others. So for today, I want to start with a little bit of background on just looking at causality from an information theory perspective specifically, and then even more specifically from an information decomposition perspective. And then I'll talk a little bit about the methods and results from this SURD paper, and then kind of bring it back out into looking at causality from a modeling perspective. So we're going to think about causality in terms of information theory metrics that we can apply to time series variables. So we're going to think about observational or modeled time series variables and the entropy or uncertainty of those time series variables. And a good place to start is transfer entropy, which is a conditional mutual information measure. And it's basically the information that the history of a source, let's call that source X, provides to a target that's conditioned on already knowing the history of the target variable. So here we have kind of our classical Venn diagram where these circles illustrate the amount of entropy of different random variables. And Y is our target, and transfer entropy is this kind of green slice here. So the mutual information is a green and an orange thing, so it's the overlap between a source and a target variable. And the transfer entropy is conditioning on the knowledge of the history of the target, which is this circle right here, and that kind of leaves us with this piece. So we can use transfer entropy as kind of a corollary of Granger causality and apply it to time series variables. And there are a lot of examples of process networks of time-dependent interactions between pairs of variables. So that's really useful, but there's a few restrictions of transfer entropy. Generally, it's restricted to sort of a pairwise view on causality. So typically we're looking at the transfer of information from one variable to another variable, or one source to one target. And there are several ways to extend this to a more multivariate context, which also allows us to consider things like confounding variables, colliders, and mediating variables that are all examples of cases where you have at least 3 variables that are interacting. Another thing about transfer entropy is that if we look at what it is, and it is a conditional mutual information measure, it's actually composed of unique information that X provides to Y, but it also incorporates an aspect of synergistic information that only arises when you know both the history of X and the history of Y at the same time. So this is used to explain this kind of middle component of this Venn diagram, which is interaction information. And interaction information can either be negative or positive, which means that transfer entropy can either be greater than or less than this mutual information quantity, which can be a little bit counterintuitive at first. So then moving into what is this uniqueness and synergy that's kind of embedded in transfer entropy. This paper from 2010 has been pretty highly influential, and it is kind of exposing this non-negative decomposition of multivariate information. And mostly it's talking about multivariate as in 2 sources and 1 target. And this Venn diagram here is now a Venn diagram where the circle is the total mutual information from 2 sources to 1 target. And you can split it up into a synergistic or joint, and a unique or individual from each source, and a redundant or overlapping component, such that these components add up to this total mutual information. And it's convenient that these components also explain other existing information theory measures. So if you think about transfer entropy or mutual information or any other conditional mutual information, you can explain those information measures in terms of these components. One caveat to this is that, these are kind of nice to interpret, and they help you understand why, certain information quantities are the way they are. But really what we have here is 3 equations and 4 unknowns. So we can't just directly solve for these components using information theory. So we need to define one more equation, and usually people start with a metric for redundancy. And I'm not going to talk about that in much detail, but just to put that out there, is there's no be-all end-all way to actually perform this decomposition. This decomposition also applies to higher dimensional systems. So A is showing the 3-dimensional or 2-source 1-target system, and B is showing the same decomposition, but if you had 3 sources and 1 target. And obviously it's, do you want to ask a question, Hoshin? I think you're on mute, or at least I can't hear you.
If you want to finish your thought, yes, I'd like to ask a question, but.
Sure. Yeah, I can just finish this, this kind of idea. So if you think about a system with 3 source variables, you can have basically any combination of unique information from a single variable. You can have redundant information from any pair, or all the triplets, the single triplet of source variables. And same thing for synergistic information. And kind of on top of that, you can have cases where, say, sources 1 and 2 provide information synergistically, sources 2 and 3 provide information synergistically, but they are redundant with each other. So you can have sort of synergistic redundancies and kind of weird information terms that become difficult to interpret. Go ahead, Hoshin.
If you could go back 1 slide.
Yep.
So you identify these four components. I'm not sure how to phrase this. Just so I can have an understanding of what you're meaning by information. Is it reasonable for me to think of this as, when you say information, that you mean information in the sense that if you know all four of these components are useful for predictive purposes, or is there some other nuance or aspect of what you mean by information or the utility of this information that I'm missing by just thinking about predictive, or is there something else? Yeah.
If you're just thinking about predictive information, I would say it's all the same. So I mean, you could consider, like later on, we'll talk about, this is the information that these two sources provide to the target. There's a larger circle here that is the entropy of the target. Right, and so the two sources may not provide, that they may not completely reduce the uncertainty of the target, and to the extent that they do,
Well,
that's quantity.
Yeah, no, when I say prediction, I mean the entire thing, predicting the entire evolution of the uncertainty. I didn't mean just predicting the mean, but okay. So, but are you saying that you're talking about information from the point of view of being able to, as best as possible, quantify your predictions with a particular uncertainty, or is there some other aspect of this which, for example, has to do with improved understanding of the nature of the system? Or am I missing something if I only think about this from the point of view of prediction?
From the point of, what did you say, from the point of view of the prediction of the uncertainty of the system?
Well, when I say prediction, I can think about predicting the evolution of the system, including its entropy and its uncertainty, right? That's a predictive perspective. But because you're talking about causality and so on, I'm assuming that there's also some other aspect when you talk about information which has something to do more with understanding the underlying nature of the system or the structure of the system,
right?
Independent of this problem of prediction. Yeah.
I think maybe it's along that lines, because I guess later on, I want to tie it into the idea of predicting, and hypothetically, if you are correctly representing, if you're representing these underlying interactions and you know what they are, you should be able to make a better prediction. So it's not like they're not related. But in terms of, like, if you just do the act of doing this breakdown does not, like, improve your ability to make a prediction.
Okay.
It does tell you something. It does tell you something about how the variables are interacting in a way that one of them is providing information, or both of them are providing information, and, like, what do you really need to make that prediction?
Okay.
Is kind of more clear.
We can come back to it. Because I think this closely ties into something I'm very interested in. So let's get back to it later.
Yep, sounds good. Right, my thing here is that it gets really complicated. So just expanding to 3 or 4 or 5 variables, you can see how many different kind of components there are. Some literature refers to these as information atoms, as in kind of like the smallest. You drill down the mutual information into its individual components or atoms, and these atoms all make up this whole of the total mutual information. So this kind of becomes difficult to interpret, for one thing, and it's also difficult to estimate. So even if we could kind of confidently have a way to get all these different components, it's a question of, is this useful, and what do we want with these? It'll easily get into the hundreds of the numbers of components that we might have. So I want to look kind of briefly at some different, what I'm going to call coping mechanisms. And by coping mechanisms, I just mean ways that people have applied information decomposition in a way that they don't have this kind of issue. So you figure out a method and an interpretation of a way to use information decomposition for causal inference. So the first one is mine, and I can call it awkward because it's mine. And basically what I did during my PhD is said, I just really want to look at pairs of sources. I don't want to go far beyond that. I just want to look at a network of, say, 10 source variables that might provide information to a target. but I'm only looking at them in a pairwise approach. So I'm taking every possible pair of variables. And then what I'm doing is I'm looking at, for a given individual variable, paired with any other variable, with what variable does it provide the highest and lowest amount of redundant information, or the highest and lowest amount of unique or synergistic information, and kind of like using that ranking to sort of assign a network of dependencies where pairs of sources can provide redundant or synergistic information, individual sources can provide unique information, and it's kind of based on looking at all the possible pairings of the variables and extracting kind of minimums and maximums of those information quantities. So that's one way. Another way, this is work by Peishi and Praveen from his PhD thesis, and what he did is he looked at a more truly multivariate context, where he has basically a directed acyclic graph approach. So this image here is showing a directed acyclic graph where he has kind of pre-applied a conditional independence testing to select these particular nodes that are influential to this target variable, which is still a highly multivariate system. So he's looking at different time lags. So along the horizontal, we see time lags, and on the vertical, we see different variables. And then he is somehow subsetting those into two different groups. And this illustration is showing that he's doing it by time. So he's showing immediate time lags versus more distant time lags. And in this group, this image is kind of a more generic idea where you are just kind of subsetting your variables in some way. And then once you have two subset of variables, then you can do information decomposition the same way I was doing it, where you just have a pair. So you just have a unique information from one subset, unique information from another subset, redundancy and synergy in the subset. So basically this enables a multivariate mutual information measure, but still you're using kind of a bivariate approach to the actual information partitioning. Another option that I came across a couple of years ago. This is a paper that I actually presented as part of this reading group maybe a year or two ago. What these guys did was they don't explicitly do information decomposition, but they instead consider information quantities from differently sized subsets of source variables. So basically they look at causality from the standpoint that if you have, say, n number of source variables to a target, you could have individuals, pairs, triplets, and the quadruplet, and all of those subsets can provide information to the target. So this image is an example of they applied their method to drivers of El Nino, and so they used some climate variables, and I couldn't tell you what these are now, but basically the percentages are percent breakdowns of attributions of causality from individuals, which are inside the circles, 2 links, which are connecting pairs, 3 links, which are connecting triplets, and 4 links, which are including the whole system. So basically a 1 link, which is these individual contributions, are interpreted as unique, and any of these 2 and 3 and 4 and 5 and 6 and so on links are interpreted as some combination of redundancies and synergies within the system, such that that information is separate from information that you could have gotten just from knowing an individual of these drivers. And then finally, the paper, kind of bringing us back to the paper for today, this paper about decomposing causality also considers all subsets of sources kind of similarly, but it goes a little bit farther and explicitly estimates a redundant and a synergistic and a unique decomposition from those. And I'll talk a little bit more about its method, but basically it uses a specific information and a ranking mechanism to do that. And this is kind of what I was talking about when I was trying to describe to Hoshin. This is their version of this Venn diagram where the interior is synergistic and unique and redundant, information. So this is the total mutual information from sources to a target. And then this outer circle is the uncertainty of the target variable itself. So they also consider, they start with the total entropy of some target variable. And then these are different kind of simple examples where they are just showing how their method works. And I'll talk a little bit more about that. Okay, next I want to talk a little bit about the methods in this paper without going terribly into the weeds, but feel free to ask any questions. Okay, so from the standpoint of this paper, they decompose the entropy of a target variable. And the notation here, basically QJ is a single time series variable, and the plus indicates that it's the future. So it's basically like one time step, like the next time step. Whereas all of the source variables are at the current or any previous time step. So this is the entropy of our target variable. And the first component that's kind of the easiest to understand is what they call a causality leak, which is kind of interesting. They call it a leak, but it's just the missing information, basically, that the source variables don't provide to the target. This is also the same thing as the conditional entropy, or you can call it the aleatory uncertainty. So this is information that's not there. So it's just the leak. Meanwhile, these other components are, you see this R, U, and S. This unique information is a summation over 1 to n, and n is the number of source variables. So basically this is saying that unique information is summed up over all of the individual sources. And these redundant and synergistic components come from any subset of variables. So here we're changing our notation a little bit, but here I is indicating a subset of variables. So any pair or triplet or quadruplet of possible source variables. And just as a reminder, these three things here add up to the total information, so that the total information is decomposed, and then you can kind of go further and decompose into these kind of subset terms. Okay, so kind of being non-specific about specific information quantities, each of these terms within the summation is an expected value of specific information, and specific information is information about a particular instance of your target variable. And so specifically, if you take one of these, so just imagine this as being one subset, so like, some pair of variables. This is an expected value of this, and what this is the specific information component. So I imagine specific information as like, you have your PDF of your target variable, and you're just taking a slice. So you're kind of like taking a slice of your higher dimensional PDF along the axis of that particular instance of a target variable. But we still don't really know what these are because they're labeled R, U, and S. So we'll get to that next. But in general, this is the definition of specific information. And I find the easiest way to think about it is with this down here on the right, where you realize that we can basically reconstruct mutual information. So this is the total mutual information between all of the source variables which are embedded in QI. So whatever subset we're thinking of, so whether it's 2 or 3 or 4 variables. So the sources to the target, we can take a summation over all of the possible instances of the target of this specific mutual information measure, and it will add up, or the expected value will be the total mutual information. So that's kind of what I mean by a slice, is that you have this probability density estimation function that gives you the total mutual information. You are kind of looking at like a particular slice associated with a certain target outcome. So that's specific information, but we still don't know what these pieces are. And in the paper, this is what it says they are. This meant absolutely nothing to me. I just couldn't read this at all. So we're going to move on from this and look at it a little bit more graphically. But I don't know, math language, maybe this is easy to understand. The way that I really understood it was looking at this figure, where first what they do is they compute specific information for all the different subsets. So here we have subsets of size 1, size 2, size 3, size 4, and this is a system with 4 source variables. So they compute all of the slices of specific information for a given instance. So this is like a single slice right here. They then rank them. So within each subset category, they rank them from lowest to highest. And they then take the individual sources and consider that this lowest one, so this happens to be information provided by source number 4, is the lowest, and they call that amount redundancy between 1, 2, 3, and 4. So they say that's the amount that's redundant in the system. The next highest is just redundancy between 1, 2, and 3. So 4 doesn't provide it, but 1, 2, and 3 all do. Then 1 and 2, and then this last component is unique. So that's all of that. That's it for redundancy and uniqueness. And then they draw a horizontal line, and all of these next values are get attributed to synergistic effects. So these are information that the 2 and 4 provide together that is not embedded in whatever is provided by any individual variable. So they call that synergistic. And this is just for one slice, and so they do it for every slice, and then you add up the common terms. So you find all the R 1, 2, 3, 4s and add them all together. You find all the synergies between 1 and 2 and add them all together. And that's what this term is. So that's what, when you have a certain subset, so say 1, 2, 3, you're just adding up all of these 1, 2, 3 values to get this total redundant or unique or synergistic information from any given subset size. So that's kind of the method. I'll talk about a couple of pros and cons of this later. But first, I just wanted to go through a couple of the example results. But any questions or comments before I move on? Okay. So the main point of this paper is, okay, we have this method, we're gonna apply it to all of these different test systems that have a pretty good variation. Like there's examples of multivariate, bivariate systems with confounding variables, systems with different time lags, synchronized systems, stochastic systems, kind of a range of different systems, and they compare SURD, so this one is theirs, with several other causal inference methods, some of them based on information theory measures, some of them not, and basically they claim victory in the all-around competition of they claim that their method correctly elicits the causal graph that because all of these are cases where they have a kind of pre-constructed causal relationships. Meanwhile, the other methods, do better on some types of systems or other types of systems, but this is the only one that they think captures all of these different types of test cases. So I'm not going to talk about all of these. I've just picked a couple to kind of illustrate what they mean. And this one is a pretty simple example where they have what's called a collider variable, and they call this a synergistic collider. So they have Q1 as a function of both Q2 and Q3, and Q2 and Q3 are autoregressive, basically. So they're just they are only paying attention to their own history, and there's some noise terms. And basically what this method finds, these are all the different possible components They find that if you look at information to Q1, they find a dominant synergistic term from 2 and 3, which is basically saying that Q2 and Q3 are providing synergistic information to the target variable. And meanwhile, 2 and 3 are only receiving unique information from themselves, so from their own histories. And they're also showing this is the leak. So 0 leak means that the sources 100% reduce the uncertainty of the target variable, and a leak of 100%, so 1, would mean that basically the lagged history isn't providing very much information at all. And so they must have these noise terms must be pretty large, because the leak is really high in terms of, I guess, yeah. So source 1, the noise term is a lot smaller than 2 and 3. So correspondingly, the causality leak is a lot lower, and 2 and 3 are kind of less predictable, I guess you could say, based on knowing these lagged variables. And then these are the results for the other 4 methods. So they're not broken down into these different components. So basically, the extent to which information comes from Q1, Q2, or Q3. And you can see that some methods capture this type of thing, basically that 2 and 3 provide the information, and convergent cross-mapping is the one that specifically doesn't. This is a similar example, but now we have a confounder. So instead of one target having 2 different sources, now we basically have one source with 2 different targets. So Q1 and Q2 are both driven by Q3. And when we just look at the top, so we look at information to Q1, we see synergistic information provided by 1 and 3, which correspond to our determined system, and also unique information from Q1. And then similarly, the other methods kind of capture that or don't capture that in varying extents. They then so they have a lot of these kind of test examples, and this is kind of an example of, okay, now we're going to apply this to experimental data. And they use a wind tunnel data set where they have turbulent boundary layer flow from a wind tunnel. And what they do is they have this big data set, but they just choose 2 points. So they choose one location that is in the inner boundary layer and one in the outer layer. And they're basically testing to see whether the inner layer is providing information to the outer or vice versa, or if they're unrelated. So they're taking time series data from these 2 individual points. And what they find is that the inner layer and the outer layer both receive information from the outer layer. And they refer to that as a top-down causality, where the turbulence at the outer layer is influencing the inner, but not vice versa. And that matches up with some fluid dynamics hypothesis that they discuss, which basically is a hypothesis that is how the information should flow, is kind of top down rather than bottom up. However, I kind of notice, and they do talk about this in the paper, that there's a pretty huge caveat here, where the causality leak is just enormous. So this is 99%, which is saying that these information components, they only represent 1% of the uncertainty of the target variable. And they basically say that, well, we only choose 2 time points, or we only choose 2 points in this whole system, and we also only looked at one. I think they only looked at 1 time lag. So there's a lot of kind of, this seems ripe for a more multivariate type of approach, but they're just kind of using it with 2 points. Go ahead, Hoshin.
So in none of these estimates, they provide uncertainty bars on these estimates. On
the information components?
Right.
No. And I'm not sure how, I'm not sure how they would, yeah, I couldn't tell you about statistical significance either. I'm not sure what their method is. Like usually there's some statistical significance method.
But in principle, when you estimate anything, you should be able to calculate some uncertainty bounds, right? Presumably.
Probably, yeah, there's
Okay.
yeah, go ahead, Teishi.
Yeah, so I haven't read this paper, but I have read his other papers before. I remember they used the binning-based method to calculate different components. So the uncertainty will be associated with how they do the binning to calculate the probability. So
Mhm.
actually, I have a follow-up, not quite kind of question, but more a comments. In the previous slide, showing that the CCM is pretty bad. I think this is well, is this
I think
that-
this example, yeah, this example was kind of like CCM didn't capture
yeah.
it.
Yeah, I think this is kind of expected because I recall that CCM is developed for the deterministic system, while this system has the noise term there. So CCM is expected to
Right.
not that great. But I'm a bit surprised on the last example you showed.
This one.
Yeah. The PCMCI is pretty bad because the PCMCI is a kind of generalized method for the multivariate transfer entropy. Since the second one, the CTE performs pretty well, I would say. I would imagine PCMCI should be similar to CTE. Maybe they didn't configure the PCMCI in a thorough way, I think.
That was kind of my hypothesis, was that PCMCI, that this is such a small amount. So it's so much noise and so little dependence that it would be easy for any method to call this not significant, or to like not capture it in the first place, because it is such a weak connection.
Yeah, I think that in PCMCI there's a lot of statistical significance tests. So maybe that leads to all the zero values, they put the threshold pretty high.
Yeah, that's probably right on.
Thanks for clarifying, Peishi, about the binning method, because my own investigation of binning suggests that binning is a highly unreliable approach to calculating entropy. So that would be worth looking at.
Yeah, they actually they don't talk about really their PDF estimation method in this paper, but they reference transport mapping, and I just didn't get a chance to look into what that was.
Yeah,
I'm
so
not-
I read his physical review paper a couple of months ago. So I was trying to figure out how he calculates these information metrics. Essentially, he mentioned in one sentence he's using binning method. So
Oh, okay. Okay, in this paper, he mentions in one sentence transport maps.
Oh,
There is a reference. So I need to just dig to the next reference, and what's that? So
Okay.
I literally have no idea what a transport map could be.
yeah, because if you read from like how he calculates the information metrics, he basically starting from the specific information, which we also deal with a little bit, right? So to calculate this, the best method is to use the binning-based method to calculate the probability at each binned, at each cell.
Yeah, I think that's a feature of this technique that I think that you can't use your method, right? Like you can't use k nearest neighbors or something like that.
I don't have an objection to using binning, but if you don't do it properly and robustly, when I gave my talk a few years ago, I looked into binning and I looked into the theory of it, and I looked into the uncertainty associated with the probability estimates of binning and how they translate into uncertainty of the entropy estimate. And it's horrendous. I mean, it's pathetic. And people seem to ignore that because I don't think anybody else really looked at it. But I do think that you could continue to use binning, but you can use more robust processing of the information to tamp down that uncertainty. We just haven't spent any time talking about it as a group. Yeah.
Yeah, so these methods may be more or less comparable depending on the effort that they spent, aligning them in terms of those types of decisions.
I just point out, if you go back to your one where you were showing the decomposition, where you start adding, these terms, right?
Yeah.
So, I mean, just look at this. If you start with the first term, then you're assuming that that first term is accurately estimated. Now you
Right.
go to the second term. So any uncertainty is going to be projected into the second term, and then it's going to compound with the third and the fourth and fifth and sixth and seventh. So you better be very, very careful about how you estimate these quantities. Otherwise, you're going to get garbage. Right?
Yeah, and that's an issue that another thing that I hadn't thought about, but beyond that, I think there's a little bit of a assumption that they're making regarding just calling this redundant in the first place.
Sure. That's a conceptual idea, but
kind of a separate, issue. But yeah, thanks for that comment. Right. Okay. So yeah, a few pros and cons of this method. They're all about the pros in the paper. So the first two are cited from the paper. Components are non-negative and they add up to the total information by design, which is great, such that the information components plus the leak do add up to the total entropy, and you can disaggregate them in different ways to satisfy other mutual information measures at levels of smaller subsets, if that makes any sense. So that it's kind of, it conforms to the laws of information theory, I guess, is what you could say. Based on examples, it captures a lot of types of interactions, at least as well as other methods. And it also provides an extra level of detail regarding those causality types. So to the extent that you are wondering whether your interaction is redundant or synergistic, it does provide that detail. And I didn't really talk about it here, but they also have examples where they show that they capture particular time lags of interactions. Besides that, some assumptions and potential pitfalls, in addition to that aspect of reliance on binning decisions and uncertainties kind of building up with the ranking. It does follow what's called a minimum mutual information assumption. And I won't, I've probably beat this into the ground previously, but basically it's assuming that two sources that individually provide the same amount of information must be redundant, which you could agree or disagree with that. It also leaves out some components in that really complicated redundancy lattice. So those hundreds of components that I was talking about at the beginning, it does kind of automatically not calculate some of those, which means that those components are kind of lumped into other components. So those are some simplifications that occur that are kind of depending on that ranking algorithm that tell you, this information component is higher than this, therefore we're going to call all of this redundancy. But on the other hand, this method still does get pretty cumbersome if you do have more than several sources, just because it does rely on those subsets of possible variables. Go ahead, Hoshin.
So that first assumption, strictly speaking, would only be true if you removed one of the sources and nothing changed.
Right. Yes.
Okay.
Yes. Yeah. So if you're familiar with like the die roll example, where say my target variable is the sum of two die rolls, this method would say that the individual die provide some redundant information because they provide the same amount of information, where I would say, oh no, those die, they actually provide unique information, because if you got rid of one die, you don't compensate the information from just knowing the second die. So it's kind of a disagreement about the amount of information versus what information, I guess is what you could say. But yes.
Because of the concavity of the information, doesn't that, like in that sum of die rolls example, doesn't that redundant information go to synergistic information if you don't consider it to be redundant?
Right. Yes, some of it goes to, well, in the minimum mutual information scenario, you would say that mostly it provides synergistic information, and then it provides this wedge of redundant information. So the redundant information would be equal to the information from one die to the target. And then if you said, no, none of that information is redundant, then you'd still have a lot of synergistic information. But you'd have two unique components of information.
Right.
So you have synergistic information either way, but
Yeah,
But
that's kind of what I'm often most confused about by this Williams and Beer kind of thing. It seems like this redundancy and synergy thing is quite counterintuitive to what we actually mean by synergy and redundancy. Like, shouldn't we actually be decomposing the variance instead of this information? Like, wouldn't that be more interpretable? I know there's some paper, I can't remember the authors, but they suggest that, given some Gaussian examples, that actually decomposing the variance makes much more sense than the information.
But in the Gaussian case, the variance or the standard deviation is directly through a log transformation related to the variance.
Yes, but this log transform really screws up the interpretation, actually. So you get this synergistic information even though you're just adding two Gaussians. And that doesn't really make sense in terms of, like, there's no actual kind of a synergistic effects in some linear regression model. It's just two separate additive effects.
I'd have to walk through it with you specifically for Gaussians, but my sense is that log sigma is intuitively a better indication of uncertainty than sigma, in the sense that it's additive, whereas sigma relates to sort of a multiplicative relationship. But
I'll try to find the paper that I'm referring to.
Okay.
Send it in the chat.
Okay. Since we're on this topic, Allison, do you mind if I push you a little bit more to
oh no, yeah.
help me understand? So previously you were talking about rolling two die and adding the two together. Yeah?
Sure, yeah.
Sum of two die. If I change the problem to the averaging the values of the die, okay? So it's so 3 plus 4, and I take half of it and I get 3.5. Okay. Could you help me now understand how you would interpret unique, redundant, and synergistic information in the context of this modified problem? Yeah.
I think I've not thought about that specifically, but I think that if you took the average of your two die, your distribution is very similar, or it's the same. It's just shifted. So I think you'd get the same decomposition for the average that you would for the sum. But if you thought about like the multiplication or something, you'd get something different. Go for it, Peishi.
Yeah, I was thinking that Hoshin, when you mentioned the averaging, it's remember there's a unique kind of hot topic in causality, is that whether the causality still holds if you aggregate information across space and time, they will change. Right. So some interactions, for example, in a very fine time scale, I mean, if you aggregate it to look at the yearly data, they may not necessarily dependent on each other, just from a statistical perspective.
Yeah, yeah, I'd love to walk through that, because when you average something, the definition of what's unique is somewhat different, right? And um,
Um,
it's a little more complicated, it seems to me.
um, I think mathematic wise, like if we dig into like still look at the specific information, that probably would be initially the specific information would be the probability of some variable at a particular time, say at per hour. And then you aggregate it, it will be the probability of this variable per year. And so it won't be the same anymore, but still we're looking at synergistic redundant information. But the information at that time or spatial scale, they may behave differently.
Oh, okay, I don't want to stop you here on this, Allison, but it's that simple example like that, which I think could be incredibly revealing. It would be interesting to know if they ran their test or these different tests on just that very, very trivial example of what would happen.
Yeah. Yeah, maybe there's something I'm not thinking about, or maybe it really pops out if you wanted to average 3 variables, or if you have different structures.
Because
Yeah,
Pacey's right, in physical modeling, we have to deal with aggregation all the time. So
yeah. Yeah, so that brings me into my very last thing that I kind of wanted to link this to a potential use for if you were interested in modeling and asking questions about why models are behaving the way they are. So I just wanted to give a couple of examples. So probably a lot of us are familiar with this this question of, do models use available information? And kind of a follow on to that question is, if they do or don't use it, then how, or what information is it that they are or not using that's available from their forcing data. So this bar chart is kind of a lot similar to the Venn diagrams, except now the entropy of our target variable is going to be this entropy of our observed something that we hope to model, and this mutual information is the mutual information between sources and the target. And this is kind of what the paper is calling this causality leak, or missing information that the sources just don't provide to the target, right? And then on the other hand, we have this lower bar is information that's actually resolved given our model, and this is information that the model is missing, right? So this is information that the sources technically provide regarding the observed output, but the model is, for whatever reason, not kind of not living up to its fullest potential, right? So to the extent that a model uses or doesn't use that information that is available to it, a follow-on question is, how does it capture observed causal relationships? And we're going to call this kind of generally functional performance. And this is an example of a paper that explored functional performance from an information theory perspective. And basically A, B, C, and D are different models. And we're plotting predictive performance versus functional performance kind of hypothetically. And model A is kind of the thing that you might expect to happen, where as you change a parameter, let's say, you change your model performance, and hopefully as you improve your predictive performance, so you go down vertically, hopefully you also go in towards 0 on your functional performance scale and have better predictions and better functional performance, or better replication of some type of causal measure, right? Meanwhile, you could have other types of models, hypothetically, that might not actually have that behavior, where you could have some potential trade-off where maybe you improve your predictions, but at the cost of, trading one process for another, or vice versa, where you might improve your causal interactions, but you don't improve your model performance. So this kind of got me thinking about a weird thing that everyone's probably thinking like, duh, but it's the fact that the however a model behaves. So you know, so whatever evaluation measure that you want to use about your model, it's dependent on obviously your model structure. So whatever your equations and parameters are, but also your sources, and not just your sources, but the interdependencies between your sources. So your sources, the extent to which they're related to each other actually has an implication on how those sources are interpreted through the model structure and lead to some model behavior. So we asked some kind of weird questions like, what types of interactions can a model possibly represent? Can this vary depending on how sources are related to each other? And basically, we ended up looking at functional performance along an axis of source dependency, and how a model is behaving as its inputs are not varying in terms of magnitude, but varying in terms of interrelationships. So correlations, I guess you could say, between the sources. So we looked at a bunch of different kind of like a buildup of examples from a binary kind of super simple case to kind of what we're thinking of as like an actual model example. So the first thing that we did was just a binary example. So this is a binary 3-variable system. X and Y are somehow combining to produce Z. So Z is our target. And if you're thinking about a binary PDF, there's binning is pretty easy. So that was why I chose this, was because you just have kind of eight different bins, 2 by 2 by 2. And basically we made X and Y range in terms of being totally independent to being completely dependent. So basically being copies of each other. And we applied different models or different logical operations on X and Y to produce Z. So for example, we could have an AND relationship where Z is 1 if both X and Y are 1. We could have a binary exclusive OR relationship. We had to have a case where Z is equal to Y and is not dependent on X at all. So we kind of sever this connection. So basically we have a whole bunch of different ways that X and Y could be related and a bunch of different models. And we can ask what types of information in terms of information decomposition components can we get from this? And that's what this is showing. Ignore the colors here, but the columns are different models, so different logical operations, and the x-axis in all of these figures are mutual information between the two sources, ranging from 0, which is independent sources, to 1, which is where sources are collapsed and they're completely redundant with each other. And we see that for the first kind of main thing, model structures are differentiable. So a model might be limited in terms of it can't produce. So there's no observed data here. These are all just models. There's no observation. But if these were models and there was some kind of like observed truth that we're comparing them to, any white space in this graph kind of means that this combination of synergy and redundancy and uniqueness wouldn't be possible given that particular model structure and given that particular dependency between sources. So this is just kind of to illustrate how a model structure determines information components, and then the interaction between the two sources also determines kind of the possible range of things that could possibly happen. So that's not really a model example, it's just an illustration. And then I'm gonna not talk about all the other examples. But basically what we did in the end was we took model output from Andrew Bennett's one of his PhD papers, where he looked at,
Sorry,
oh, yep, go ahead.
just to go back to that one.
Sure.
I know you're downplaying it, but I just want to point out that because any computational process can be represented using logic gates, I don't think you should downplay the importance of this.
I mean, I thought it was cool, you know.
Because it basically points to how these kinds of computational processes lead to changes in SR and U, to the extent that we're interested in that. And my understanding is that the universal gate is something called an XNOR gate, XNOR.
Okay.
It might be interesting to run it for that case, because apparently you can construct any other logical operation by combinations of XNOR gates. It turns out, so it's kind of like called this universal gate. Anyway, I just wanted to mention that.
That's interesting. I don't know what XNOR what that means. Like what does it look like in terms of
So you take OR and then you negate it, so you go not OR, and then you make exclusive not OR. I forgot now exactly what it is, but yeah.
Okay, that's interesting.
The
cool thing in this example was the binary XOR is really often used as like an example of like, here's synergistic information. So pretty much any paper that talks about synergy is talking about the binary XOR. And it is really different from all of the other possible types of binary operations, specifically in how it can produce synergy. And how it can produce complete synergy, and it can produce complete synergy across a wide range of mutual information values of the sources, which is also an interesting thing about the binary XOR operation. And then some of these other ones kind of collapse into each other, like they look quite similar to each other. And the reason I'm highlighting these covariances as the colors is I'm showing how you can kind of also use covariance to distinguish between these different cases. But yes, this kind of, because I previously had done this kind of naive thing where I was like, I want to generate a PDF, like I just, no data, just I want to generate a probability distribution function that can reproduce. I want to prescribe synergy, redundancy, and uniqueness and make a PDF that elicits that combination. And I realized that I couldn't do it with certain combinations. So I'd say like I want 0.5 synergy and 0.3 uniqueness and 0.3 uniqueness from this other variable. And I like couldn't get my pretty bad algorithm to give me a PDF that obeyed that. And then this kind of led out of that because I realized that, yeah, like the structure of your model might be, maybe it is impossible. So like maybe, every combination of these types of information isn't actually possible.
Sorry, I misspoke, Allison. I just looked it up. The universal logic gates are NAND, not AND, and not OR.
Not AND, not OR.
Yeah, just Google it, but you can construct any other logical operation just using not AND and not OR gates.
Yeah, thanks.
I mean,
yeah, this
either only not ANDs or only not ORs. I don't mean both. Like each of them is a universal gate. Yeah.
Okay.
Yeah. Sorry.
Yeah, so how we kind of were like, okay, we have to apply this to an actual model. We use SUMA, and these are model outputs that were already developed. And basically this is a process-based model, and then these two are gonna be process-based models coupled with a neural network. And what we did was we specifically wanted to look at how, and there's a bunch of flux towers that this model has been applied to. So we have, the validation data and all the flux towers kind of right there for us. And the specific question that we asked is, how do air temperature and relative humidity provide information to the Bowen ratio? So we just combined sensible and latent heat flux, and we're just looking at this 2-source, 1-target system. Across a spectrum of possible interdependencies between air temperature and relative humidity. So the x-axis is showing source dependency. So this is independent sources, and this is highly dependent sources. And then the y-axis is showing a functional performance measure that I won't talk about, but basically this is kind of lumping synergistic and unique and redundant replications between the model and the observations together. And lower values are better. So a low value where these stars are is better. And what we found was that the time windows when the model was applied where air temperature and relative humidity were less dependent, had worse model performance, and model performance was always better for every model when air temperature and relative humidity were more synchronized, which kind of made sense. And basically we kind of interpret that as models are using that redundant information easier. So when there is more information that the sources provide that's redundant, it's more likely that the model will get that information from one or the other source, and it doesn't matter because they're redundant. Whereas if sources are more unique, models have more of a problem. And the interesting thing with the comparison between these models was that this SUMA bidirectionally coupled neural network really had the best behavior at the 4 independent sources. So it had a lot better performance, specifically when we have this kind of like challenging time when air temperature and relative humidity are less related to each other, which is kind of saying that, you know, this paper is, you know, finding that this coupled neural network is able to improve upon this process-based model. And this is kind of saying something about why or when it's making those improvements, and it's doing it all the time, but specifically when we have cases where air temperature and relative humidity are providing maybe more unique or synergistic types of information. Yeah, so the main conclusion there is that, you know, dependencies between sources also impact how their information gets used within a model. And I have no real like good conclusion, but these are just some open-ended things. Basically, there's a lot of different causal inference methods out there. A branch of those are information theory based. A branch of those are based on information decomposition. I've seen an increasing number of papers kind of like this that are comparing between methods with all these test cases, which is a good thing. Also just the aspect of there's these highly multivariate systems and they all have this kind of information decomposition has this kind of combinatorial issue of a lot of different possible subsets. And your best coping mechanism might really just depend on what the question is. So there might not be kind of a be-all end-all decomposition mechanism. It might be depending on what is actually the question that you're asking. And finally, these causal inference methods are largely applied to test cases where you know the causal graph and observational systems where we're trying to learn the causal graph. And extensions to modeling are kind of an in-between case because technically our model is something that we've made, and so but it's often complex enough that we can't just draw the causal graph exactly the way that we would with one of these really kind of simple test cases. So there's some opportunities to look at causal inference in the context of modeling. And yeah, that's all I got. Sorry, it went a little bit over, but I'm happy to take any comments or questions. Peishi.
Allison, could you go back to the previous slide?
Sure.
So for the different combination of the air temperature and relative humidity, how did they get these different, you know, realizations of TA and RH as the different pairs?
That's a good question. We have a lot of flux tower. We have a lot of site years for different sites, and we discretized it by monthly. So we took monthly time windows of results and computed performance metrics based on those time windows. So for example, like there's some months where this was high and some months where it was low.
Have you looked into maybe whether it's related with some seasonality? Say in some months, TA and RH are more correlated and the model performs much better, while in the other months, the model performs not that well. Because TA and RH are kind of desynchronized and it's very hard to capture it. You know, it's
Yep. That's a good point. I think we did. I think this is growing season, so we did some of that subsetting, but generally yes, like this does have embedded we're not showing whether like, oh, the times where air temperature and relative humidity are less correlated is actually because it's during the spring, and that's the real reason that these are showing this behavior. That's a good point.
Mhm. And one last question is more general that I have think of for a while is, how do you think like to use, for example, your result here or other approaches to guide the model development or to do some model evaluation before running the model?
We haven't. So we there's not been any real follow-up on this. I mean, well, one thing we've talked about is it could potentially help, so say you have like a large ensemble of parameters and you have, similar predictive behavior across parameters, and that this aspect, not of source dependency, but the measure of this functional information partitioning performance could enable you to pluck out, which models are behaving the same way, or like, having a similar high level of performance, because they're more accurately replicating a certain type of interaction. But in terms of source dependency, yeah, it's kind of, sources are, one comment that came a lot in the review comments to this paper was, this is just multicollinearity. Everyone knows about multicollinearity, and it's not useful. And that was a detractor. And we tried to make the argument that, well, first of all, it's not linearity. It's kind of a non-linear version of multicollinearity. And it's also something that's not often thought of in process-based models. Like, you don't change your input data because you notice that there's a time period when some of your input physically based variables are correlated or not correlated. So that's something related that did come up. Joe?
Yeah, thanks. Could you go back to the first mention of the functional performance where you have those gaps? Yeah, there.
Yes, yeah.
Is there any assumptions on what X is in this case?
What X is?
X obs, yeah.
X opt. Where am I looking? Sorry.
Just on the plot on the left, yeah, X obs there, yeah.
X opt. Oh, I think this is inferred to be whatever sources you're inputting to the model. But theoretically, it could include any sources that you might want to input into a model.
Yeah.
So it could be also, sources that this model B doesn't use, but is it by not using it, is it going to miss this certain, aspect of information?
Yeah.
So Joe, if you think of X and Y as having a joint probability density function, whatever the dimension of X and Y is, what's meant there is if you separate out Y, how much information does the component called X contribute to reducing the uncertainty about Y?
Yeah, I'm just kind of concerned about this model structural uncertainty gap thing, because it, I mean, I guess it's still representing kind of how much the model is ignoring in the data, but that could be a good thing in some circumstances. Like, you could have some spurious variable like ice cream sales in your model that can help you predict stream flow, but should not be used by the model, right?
Sure. Yeah, this presumes that you're only using relevant information.
Right.
And so what's happening there is we're saying that the best possible performance you could get by some, for example, machine learning model, which exploits all of the information in X, is given by that middle bar. That's the closest you could come, because you're missing information that would allow you to close that gap. So regardless of how you conceived of it, that's this is a theoretical construct which says this is the best you could do. And probably even if you used a machine learning model, you wouldn't get there, but you'd get hopefully close to it. And then the other one says is if you,
But
if,
that's where I have the problem. Like, I'm not sure if closing that model structural uncertainty to 0 is actually a good thing,
may
unless
not,
we have some assumptions on xobs.
may not be. I think you could look at it this way, where in principle, all of these calculations should be done on independent evaluation data, and they have to be consistent across data sets and so on. And it completely ignores the fact that your ice cream sales might be correlated with the temperature, and therefore ice cream sales become explanatory. So none of that is considered in this diagram. Yeah.
I also have a question about like this information decomposition. I think I kind of missed the first 20 minutes of the talk, unfortunately, but I think all methods only consider like 2 variables at a time, like predicting a source, right? Or is this method different?
Let's go back. So this method actually is considering, and several of these methods are, it's considering a multivariate mutual information measure at its core.
Okay.
My method was not, but these are all
Wow.
considering a total mutual information from more than 2 source variables. And then you might look at subsets or triplets or quadruplets, but
Right.
they are multivariate.
And does the performance degrade when you're considering subsets of your inputs that are not like valid adjustment sets?
I have no idea.
Okay.
What was that question again, Joe?
Does the performance degrade of this information decomposition when the subsets you're considering are not valid adjustment sets?
What's a valid adjustment set?
Okay, no, this is actually very good because this means my next paper will be useful to people. But yeah, valid adjustment set is just some concept in causality which tells you if the variables you're conditioning on kind of give you unbiased estimates of your regression coefficients.
Okay.
Yeah, that there's no that's one thing with this paper that I think you could have a very highly multivariate source or a very highly multivariate set of sources, and it could get out of hand pretty quickly. And it's almost like you could apply this on top of I don't know why my slides aren't changing now. You can almost apply that like on top of some method like this, where you pre-select sources in some way, and then you have this kind of decomposition to ensure that it's going to be more meaningful.
Yeah.
Joe, if I could just, because you went on, I just wanted to make a final comment about your question earlier. And just to point out that that diagram from Gongwei's paper, based on work he did with me, makes no assumptions about causality. It's got nothing to do with causality. It's just purely correlational. Okay.
Yeah.
You can use it in a causal analysis, but that completely it makes absolutely no assumptions about whether X causes Y or anything. It's just these things are just they just have a joint distribution. That's all it says.
And by the way, I sent a link in the chat to the paper I was
I did.
mentioning
I got
earlier.
it. Thank you. Yeah.
Thanks.
Thanks, Allison.
So
Right.
next steps.
What was that?
Next steps.
Oh, next steps. Good question. All right, so I guess Layla is yeah, signed out. It is
Oh, sorry, I meant next steps in your research as opposed to
oh,
next
in
steps.
my research.
Yeah.
I mean I'm definitely the source dependency thing was interesting, but I don't know where to I guess it's still kind of like bivariate, and it's looking at, you know, how two sources and how their relationship can kind of, sorry, I have bugs flying around, can kind of influence a target. And I think these decomposition, these kind of like early on when I cited several of the different methods of decomposition, I think they're kind of individually really interesting. And I started playing around with a couple of them in terms of the question of, you know, do they provide you with a similar breakdown of the multivariateness of your system, and then kind of translating that to the multivariateness of your model. And kind of an interesting general question about a model is your model replicating the level of multivariate interactions that you're observing? Is kind of interesting. So
So I
kind of
like
what-
I like the part where you were using synthetic examples where you know what the correct answer should be, or in principle should be able to calculate the correct answer. I like the idea of further developing that. But I also think that given the interrelatedness on these metrics, at any point you want to talk more about that, I'd really like to see some guarantees on the robustness of the estimates, and if, you know, figuring out ways to make those as robust as possible, because your inference has become highly sensitive to what those estimates are, right?
Right, yes, yeah. And I think that's my master's student Jez is actually on here, and he's been doing some comparisons between several of these different methods, and looking at if you used these different methods to analyze the same model, like, you know, a simple model of evapotranspiration, or even like a test case,
Sure.
they tell you different dominant linkages, different, you know, slightly different timescales.
But that might be because of differences in the methods, or it might be due to non-robustness of your estimates.
Right, or just the types of systems for which these methods were made for. You know, so it's kind of like convergent cross mapping does best with these deterministic chaotic systems and type of system, and then you know, conditional.
But I'd still be very suspicious of any conclusions that are based on estimates that I couldn't trust. So anyway, if you guys are interested in talking more about how we could verify that, I did give it a lot of thought several years ago, but I never went back to the binning. And if binning is the method of choice, which it is in many cases, then we need to be sure that the way we process the data to generate those estimates ensures that you have a high degree of confidence in the result. And I can, you know, I can go back to my old notes, and I can show you that for standard sample sizes, the estimates using standard binning are just ridiculously unreliable.
To get away from the binning, can't we just like replace mutual information with a neural network, basically, like out of sample predictive power?
Yeah, if you design a neural network to do it, but then you got to go jump through all these other hoops. And I think just using binning, but doing proper statistical use of the data to generate those estimates, you can actually do a lot better than what people typically do. That's my hypothesis. I haven't run them myself, but you know, simple techniques involving bootstrapping and so on can be used to or you take the method that we developed, and then you estimate the probabilities, and then you bin them. something which is using a method that is proven to be reliable, which is based on bootstrapping and then calculates the quantity you want. Anyway, there's probably different ways to go about it.
It's a fun way to end things off. I'm curious, Allison, have you ever, I think you've cited like Virgil Griffith a bunch about like information decomposition. Have you ever looked him up?
No, I don't. Yeah, the name is very familiar though. I couldn't even tell you what his papers are exactly, but no.
He has a lot of information decomposition papers, but he's a fun character. You should look at his Wikipedia.
All right, good to know.
The other guy who talks about information decomposition in some of his talks is James Crutchfield.
Yeah, I think
You see.
you've shared some of his materials.
Yeah, but not this stuff on the decomposition. You'll find some interesting talks online, and he did a really deep dive into like information that goes from the past to the future without going through the present, and various other peculiarities of the information decomposition that you normally don't think about. Okay,
All
so
right.
Lila's not here,
Yeah.
but I guess she'll send us out a message about what's going
I'm
on.
not sure I couldn't tell you who's going next on the spreadsheet, but well, thanks for hanging on, everybody, and have a good rest of your week.
Yeah, thank you for that talk.
Yeah.
It was great to see you all.
Yeah, great talk, Allison.
Thanks. See ya.